just skip it, but sometimes you do part 1, part 2.
Hello, everybody.
Hello.
Hello.
So we were just discussing about, or maybe lamenting how there were so many harder part 2s and part 1s this year, right?
On the same hand, though, I feel like there were a lot of ones where part 2 was almost the exact same as part 1.
Yeah.
So if you finish part 1, you just changed 2 lines and you got part 2. If your code.
Let's put it more this way: there were some where like there wasn't so much time and space problems that when you just like change the iterations in part 2 or change like one variable in part 2, things worked out okay. I think there was like 3 of those or somewhere around there.
Yeah. There are a few. But
at the same time, I agree with Farouk. There were like 5 or 6 where you can't just change one thing in part 2, or at least
unless you had crazy foresight to predict that.
It's like, oh, let's optimize the crap out of this thing. But anyway.
Well,
here we are.
Started.
Let's do it.
Day 22 and 23 today, right?
All right. Let's take a look at 22 and 23.
Yes.
22. The Reactor reboot. Cubes. Oh, I remember this one.
Yeah.
Cubes.
3D cubes, X, Y, and Z coordinates.
Cubes and more cubes and nothing but cubes.
That turn on. And okay, so they give you a list of steps. So this is apparently like an infinite size reactor, right? Full of little cuboids. And they give you a series of steps that you have to perform in order to boot this reactor. So I'll go over the first step here. It says the first step is on x equals -20 to 26, y equals -36 to 17, z equals -47 to 7. And this tells you that you're turning on the cuboids or the cubes in this area. So this area is the area from x value of 20 to 26, or sorry, -20 to 26, with y value between -36 to 17 and z value -47 to 7. So those are the bounds of your cube. You're going to turn that one on. And then the next step tells you to turn on another range of cubes. And these cubes might overlap. So you got to figure out how many cubes are actually going to be on at the very end of all of these steps. And luckily for part 1, they made it nice and easy for us. They said only worry about the steps that are in the range of -50 to 50. Which for our purposes was only, I think, the first 20 lines, at least for mine.
Yeah, it's like 50
I think
cubed,
right?
50 cubed is
similar in mind.
not too bad, I guess. I don't
Yeah.
remember what that is. But yeah, so I mean, it's interesting because they have this coordinate system, but it describes a range rather than describing a single coordinate. And so you have within a single line, not only the size of the cube, but the location of the cube in geometric space.
Yeah.
But then it's not one cube, it's actually a volume where every cuboid is 1 by 1 by 1. And so what they're describing here is not a single area of cube or a single volume of cube, but it's a group of cubes in a cube shape, in a cuboid shape, in a rectangular shape. And so when they'll find a question, how many cubes are on? It's not how many of these like listed cubes that we had in the beginning. It's how many of the individual like pixels, almost, if you could think of it that way, individual units are on. And so the numbers get pretty big very quickly, especially if you start going into the next steps. But anyways, yeah, part 1, not too bad. I pretty much just mapped it out and brute forced it.
Me too.
Yeah, same.
Well, let's just take a peek at the code real quick, and then we'll go on to the part 2, the more quote unquote interesting part.
Let's jump in. I'll share mine.
Okay.
All right. Can you see my code?
Yep.
All right. Oh, I didn't put my day number here. This is day number 22, part 1. All right. So for this one, it took a little while to import my code the way that I wanted it. So I ended up using all of these different splits and maps and splits and maps and replace and include and split and map. It looks super messy and I hate the way this one looks, but the end result is a nice little array that looks like this. So I have an array of arrays, and in those subarrays, my first element is either on or off, so the instruction. The second one is another array with my x values, so the x0 or x1 and x2. The next one is the y values, so the y range, and then the z values. So this is how I wanted to import my data so that I could work through it. And for part one, this is special for part one, I spliced my input to keep only the first 20 rows, because everything after that was outside of the range of -50 to 50. So I got only the 20 rows. It looks like this. It's clean and easy to work with now. So let's get started. The first thing I'm going to do is I'm going to create a grid. So I'm actually going to map out all of the cubes that will be turned on. So I'm going to create a 3-dimensional grid in order to figure these all out. Next is I created an initialize function. So this is my function that's going to run for every step in my input. So it's going to run for row 1, row 2, row 3. So for this one, I'm going to take in the cuboid. So cuboid is just what I'm calling my input row. And next, I'm going to figure out the action. So that's going to be on or off. So that's going to be the first element in my cuboid. What am I going to do? And next, I'm getting my X, Y, and Z ranges. But for these ones, in order to work with arrays, I wanted everything to be positive numbers. So I'm shifting everything by 50. I'm adding 50 to all of the values so that all of my values will now be positive between 0 and 100. So that'll make it a lot simpler to work with, because you can't have an array with an index of a negative value. Next, I'm going to add the elements to my grid or modify my grid if it's already there. So I'm going to loop through my x values. And in my grid, I'm going to add in, well, I'm going to check if I don't already have a row in my grid, then I'm going to add a new array. Next, I'm going to loop through my y values. If I don't already have a sub array in that array, I'm going to add an empty array. Next, I'm going to loop through my z values. And now I'm going to add in that value. So if my action was on, I'm going to create an O for that value. If it was off, then I'm going to turn it into an X. So eventually I'm just going to get a giant array full of O's and X's. Because I'm going to run this now. I'm going to run a loop here to go through all of my different rows and perform my initialize function. So now I have a giant grid. Do you want me to print it out? Or we're good?
We're good.
It'd be kind of messy, I think.
We can pretty much imagine what it looked like. I think what we imagine will be more clear than
what
what
you
gets
actually
smashed
see.
into in 2 dimensions.
Yeah,
That is-
3-dimensional arrays don't look good in 2 dimensions.
No.
It's easier to just visualize it in your brain. So yeah, I have a giant grid with O's are going to be the turned on elements, X's are going to be the turned off elements. And so now all I have to do is count the O's. So I have to have a few nested loops in here because I didn't have the foresight to flatten my arrays. But yeah, oh, what am I doing? Anyways, after we count all the O's, we just have to return that. That's my count.
Cool.
This one, yeah, just brute force, turn everything positive. This was the main key, I think, for this one that I did for my method, was just shifted all to positive. Luckily, with only 50 elements, or sorry, 100 for the range, I guess, 0 to 50, 0 to 100, it wasn't that bad to just brute force. I get my answer almost instantaneously.
Cool.
All right. Did you guys have
Python?
other methods?
So
I also brute forced it. So Python. This is irrelevant. It's also irrelevant. So first, I have a different function this time to read my input from input and sample input files. So this will basically read the file, splits the string into an array by new lines and returns that array. And then I'll pass that output into my reboot reactor function, which will start here. So for this one, I'm working with dimensions again as a coordinate. So in my dictionary, I have every coordinate in that 3D or every cube location in that dictionary. For example, if there is a cube at 10, 11, and 12, 10, 11, and 12, and so on for every cubanoid, and the value will be on or off. So this is the approach I'm taking. I'm basically running through every possible combination, which is in the range -50 to 50, and turning on and off them based accordingly. Okay, so once I get my input, I will first convert them from this string, which means on, and these ranges to this array here. So my first element will be the switch with whether on or off, and I will have my X range, Y range, and Z range. So this is basically doing that and converting the string to workable array form, and strings converted into integer too. And after that, I will start looping through my input. So if any of the values are not in the range from -50 to 50, I will skip them. Otherwise, I will loop them. I will loop through them, starting from Z. Minimum X, maximum X, minimum Y, maximum Y, minimum Z, and maximum Z. So my 0 index element is a switch. If it's equal to on, I'm setting it to 1. The value for that coordinate is set to 1, otherwise it's set to 0 in my reactor cubes dictionary. At the end, I will get all the values from my dictionary, convert them to list, and filter them to keep the only ones in that list. At the end, I will return the length of that ones, because ones represent the on cuboids. Yeah, that's simple brute force. Part 1.
Well done. Yeah, one thing we didn't mention that was actually really nice about this question is the ranges were nice. The ranges always went from minimum value to maximum value. There weren't any where the maximum value came first. So I like that. It made it a little bit easier to work with.
Yeah. It wasn't that fast. I think it took around 3 or 4 seconds, but yeah, it gives the answer.
Cool. Yeah.
Okay.
Which way Alex approached it?
Wait. Nothing new. So I had a couple of misfires. I started out thinking, maybe I can just use character by character, but then I realized, that's stupid because there's some of these numbers are pretty large. So I'll skip that one. And then the second time I was going through, I was like, oh yeah, we're cruising along. And then I realized, wait a minute, these aren't actual cubes, they're cuboids. X, Y's, and Z's are different sizes. So, so then I abandoned that one too. But you can see I wrote a lot before I abandoned it. Before I realized that it was, I didn't write it wrong. Anyways, so I have a core, which is an array of an array. Again, 0 through 100, 0 through 100, 0 through 100. Initialize into 0. The first part just, chops up all the input into the way that I want them and the ranges that I want them. But then as I'm reading them, I'm also, as I'm reading each line and chopping up each line, if it's an on, then I stick it in the core, same as Scott. I adjusted everything over by 50. Otherwise, it's either a 1 or it's a 0. Kind of like, how Farouk used numbers instead of characters, but same idea. And then for me, I just, instead of getting the length of something, I just went through that entire array, and anytime it was 1, I just added 1 to a accumulating number and then printed out the number.
Cool.
Yep.
Nothing new. Very similar.
So the interesting part, of course, is part 2. Yeah. Oops, wrong screen.
I'm actually curious to see how you went about it.
Likewise.
Because this one was definitely not the same as part 1.
Yeah.
Part 1, our code did not work for part 2
So
because
part
the
2,
range was gigantic.
yeah, you notice not only are there a lot more of them, but the numbers are significantly larger.
Yeah.
And some of these, the numbers are out of order.
100,000 sounds.
I don't think that any of them are.
Yeah.
actually.
Out of order. For some reason, I thought some of them were out of order.
No, I think it's still minimum.
There's
Okay, cool.
But I see the largest numbers I'm seeing are like minus 110,000 or to, looks like about 110,000 positive and negative in X, Y, and Z ranges.
Right.
That's a lot of cubes in the middle there.
A lot of cubes. You can see by my answer. That's a big number. So a lot of stuff happens here.
Yeah.
So who wants to start with this one? And let's talk more. The code's going to be really pretty involved, maybe. I don't know how you guys did yours, but
Yeah.
let's start with approach so that we don't get too lost in the details. Who wants to start?
I can go first.
Okay.
So for this one, I did not want to have to deal with actual positions of any kinds of cubes. I didn't want to have to deal with like shapes, because if you have a cuboid and then you have another cuboid overlapping that one, your new shape is not going to be a cuboid anymore. It might be, it depends on where they overlap, but it might look like a donut. It might be a cube with a cube missing in the very center. It might have a corner cut off. It might have any other shape that is not going to be a cuboid anymore. I did not want to have to deal with shapes. I thought that would get messy and confusing. So I tried to do something else that got messy and confusing. I tried to ignore shapes completely and just deal with overlaps and total volume.
Okay.
So I figured I'm going to start at the very top of my instructions. If I turn on a cube, I know that cube's on, but now I'm going to see how much volume from that cube, how much actually contributes to the final volume of my final reactor. So I can find that by ignoring really the shapes and just getting the overlaps. So I will just kind of look into the future. I'll look at all the other steps and see if any of those cubes overlap with this current cube. And if they overlap with this cube, then I know that at the places where they overlap, the initial cube didn't add any volume to the final result from that overlap area. Does that make sense?
Sure.
So I just have to figure out, I just have to kind of loop and use recursion to go into the future for all of the different overlaps with this cube, and subtract all of those from the total volume that this cube is adding to the final.
Okay.
You follow?
Sure. So your challenge is to try to find the points at which they overlap so you can get the volume of the overlap.
Yes. And the problems that I had with this was, since I had to figure out pretty much where the overlap is, and then I had to keep going into the future and see what other cubes overlap with that and what overlaps with that. And subtract all of that volume from the initial cube. So that the only thing I'm left with at the end is the volume that that cube contributes to the final. And so I'm going to do that for all of the different steps. So obviously the first cube is probably not going to contribute much to the final, whereas the last one that turns on is going to contribute a lot, I assume, because it probably doesn't have much after it. So that was how I went about this. And I can show you the code a little later. It's not terrible, but I had a heck of a time getting everything organized and arranged the way that I wanted, where I had my, where was I subtracting? Was I subtracting inside this loop or outside this loop? Or it was confusing to do. There was a lot of different things going on at the same time. But yeah, that seemed to me like easier than actually dealing with shapes.
Makes sense.
How about you, Alex? How did you approach it?
Oh, let's actually go into your code before we forget your approach.
Okay, okay. Sure. So here is my code for part 2. It's got a lot of things that look repetitive, but it's actually not that long.
No.
So in order to do this, I pretty much just copied my old code for the imports. So I'm going to deal with the data in the exact same way. The only thing different is I'm not splicing off the first 20 now, because now I need the entire input. So now I have a few different functions here. I have get overlap points. That one's going to be really important for getting the actual overlaps. Next, I have get volume to calculate the volume of either a cube or an overlap section. And I have get overwrite volume. So that's going to be where I'm getting the volume of the overwrite sections. So the overlaps. And I have my main loop where I'm going to loop through all of my inputs. So let's start with the main loop, I guess. So right before here, I'm starting a total because I'm going to keep track of the total volume as I'm going. Next, I'm going to loop through all of my elements in my input. And luckily for this one, since I'm only counting things that contribute to the final on volume, I can ignore off statements. Because any direction that starts with off is not going to contribute to the final volume. It will contribute to the overwrites. So it will have overlaps that matter. But for my initial loop, I can safely ignore any off instruction. Does that make sense? Because it's not going to contribute to the final volume. It will take away from the final volume, yes, but it's not going to add anything to it. So now I need to get my X, Y, and Z's. So what was I doing here? Why did I only get the... Okay, yeah, so I guess I'm getting the X, Y, and Z arrays, not just the individual values. Next, I'm gonna create a cuboid volume. So I'm gonna get the volume of my current cube, the one that I'm currently inspecting for this instruction. And to get that, I'm using my get volume function, which isn't very complicated here. You can look through there. I'm just subtracting the maximum X value, but from the minus the minimum X value. And I'm adding 1 because all of these were inclusive, I believe. In the example, they gave an example like this one has an X range of 10 to 12, but actually it wasn't just 2. It wasn't just like 10 and 11. It was 3. It was 10, 11, and 12. So for all of these, I have to add 1 to get the real volume. That's why it has +1 for all of these. So yeah, and then I multiply together my X, Y, and Z's, and I can get the volume. All right, the next thing I got to do here is I'm going to add to my total volume. I'm going to add the cuboid volume that I just calculated for the current cuboid minus the overwrite volume. All right, so for this overwrite volume, I'm passing in again my X, Y's, and Z's, and I'm passing in the current index where I'm at. And so for my get override volume, Again, I'm gonna get my X, Y, and Z's. I could have done that cleaner probably. By not passing in an array, maybe.
No, it's
Yeah,
fine.
it's
You just
okay.
structure though instead
Yeah.
of one by one,
Yeah.
but whatever.
Yeah, then I need to initialize the total volume. So this total volume is going to be for the overlaps, the total volume of overlap that I'm going to then subtract. So now I'm going to loop through, and I'm looping through here for all of the rows after the initial one. So everything after I. So I'm starting with a J and I'm initializing it as I plus 1. So I want them to start with the next row. Because remember, I'm looking into the future to take away the overlap volume. So now I'm going to get an X2, Y2, and Z2. So those are the X, Y, and Z values for the next row. And remember, I'm looping through here, so I'm going to get all of the future rows. So I'm going to create an overlap. So this overlap is going to be from my overlap points. So I'm checking, do these points even overlap? And if they do, what is that overlap? So for this one, I'm using my getOverlapPoints function, which is accepting 2 cuboids and their X, Y, and Z values. So now I have X, Y, and Z for the initial cuboid, and X2, Y2, Z2 for the new cuboid that I'm checking for overlaps. So the first thing I do here is I'm checking, do the X values overlap? So in order to do this, I can check if the minimum value of the new cuboid, so the minimum X value of the new cuboid, if it's greater than the maximum value of the original cuboid, or if the maximum value of the new cuboid is less than the minimum value of the original cuboid. If that's true for any of the X, Y, or Z coordinates, I know that those cuboids will not overlap ever, so I can return null. Because I'm not going to subtract anything for these ones, they do not overlap. If it gets past all of these, that means they do overlap. So I need to get my overlap points. So for this one, it actually took me a little while to figure these ones out. I used PowerPoint and a piece of paper, and I practiced my old math skills. I started in 1 dimension, actually. I drew lines on paper and figured out, okay, this is where they overlap. Then I drew squares on paper and figured out where they overlap. And the only things that you essentially need are the corners. So you can figure out from the corners where the overlaps are. And after doing it with squares, it was easy to translate it into 3 dimensions for cubes. So essentially what I had to do was get the maximum value of the minimums and the minimum value of the maximums. If you follow me, great. If not, I can repeat that one. So to get the overlap volume, you're going to have 4 points that you need to check. So I have the minimum value of the initial cube and the minimum value of the new cube. I'm going to see which one's the biggest value of those. Next, I have the maximum value of the new cube and the maximum value of the initial cube. I'm going to see what's the smallest of those values. And that'll give me the tightest range where that includes both cubes. So I need to do that for X, Y, and Z coordinate systems. Now I'm going to call that as my X3, Y3, Z3. Those are my overlap points. All right. So now I have my overlap cuboid. So I'm going to return that. I'm returning the coordinates that overlap for X, Y, and Z. All right. So now that I have my overlap points, I'm going to check one more time. Oh, sorry. This was where I was checking if these didn't overlap, then I returned null. So now if I return null, I'm going to continue. So I'm going to continue this loop. I'm going to skip this one because it doesn't overlap. But if there is an overlap, then I'm going to run this one. I'm going to add to this total volume. Remember, this total volume is the total overlap volume that I'm going to subtract later. I'm going to add to that the volume of this overlap that I found, and I'm going to subtract from that, the overlap volume for the future, for the next rows that I'm going to run this function on. So it's a lot of different looping and recursion, and I had a lot of trial and error for where to put these different functions and where to have my minuses and pluses. This one ended up having to be a plus, this one minus, down here a minus. I had to try quite a few different things before I got it. That's why I actually left this one in here initially. I didn't just delete this because I use this for my testing. If I could get the correct answer for part one, then I knew my code was okay. So I could then run it for the entire input. So I did that a lot. I actually changed this one too. I went step by step and changed it to, let's see if I can do the first step. And let's see, okay, we got the first step. Let's try the second one. And a lot of times it broke, but eventually I got it. That was it.
Cool. I like it.
I was happy it actually worked.
Yeah.
I tried it out on paper, and actually I used PowerPoint to just create these little things. I created like a little grid with a bunch of cubes that overlapped, and I just wrote out an equation and tried to calculate the final volume of it based on like just going step by step. But it worked. It took a lot of time.
So, I mean, I think it's a very clever way to do it. And, you know, I remember you and I were talking about our different approaches at that point.
Yeah.
I think we both did our approach, but in hindsight, yours is much more elegant than mine. The volumes, yeah, I could see why the volumes made a lot of sense.
I didn't know. I knew that if I tried getting into the shapes, because if you, I'm just gonna guess if you tried shapes, like you have to consider all the different possibilities of what the new shape is gonna be.
Yeah, no, I didn't do anything outside of a rectangular cuboid or whatever.
Oh, okay, okay. Well, let's see it then.
Okay. I'm guessing no Python in this one.
Oh no.
So my approach is a bit different, but let me talk through it first so you guys get an idea. So instead of doing volumes, I did cubes. So what I would do is I would take a cube out of the list, get the second cube out of the list, kind of like what you do with yours with your recursive, right? You get one and you get all the what you call future, but basically every subsequent one.
Yeah.
They get the second one, they get every subsequent one, the third one, every subsequent one. But instead of calculating volumes, what I had done is I had taken these two, I put them together, and then one of these two, and I say one of these two because I first did it with one of them, and I was like, oh, cool. And then I realized, oh, this is not going to work for off. So I had to rewrite everything to make the first. So anyways, I think what I had done first was I had decided, oh, it'd be really easy if I took the first one because I had a running list of objects. And it's really easy if I took the first one, chopped it up and added to the list of objects. And so as I take these two and I smash these together, I find where the overlap is on each of the axes, but I do it one axis at a time. And so I'll do the x-axis first. Do I have an overlap? Well, take that back. First, I test to see whether or not there is an overlap, kind of like you do in yours.
Okay.
But if there is an overlap, I'll just do one at a time. So if there's an overlap on the x-axis, I will take that first object and I will cleave it on the x-axis. So now I have two objects.
Okay.
Right? One of these two objects overlaps, but the other one doesn't.
Yeah.
Right? So if I have two objects, let's say it merged here, I'm going to cleave it right at the borders of one. Now this half of that first object has nothing to do with the overlap, but the second half does. And I'll do it again because sometimes it's one object completely within the other object, right? And so in that case,
So
I need to cleave it twice,
Yeah.
right? So the first time I'll cleave it once, I'll have this one, I'll just put it aside because that has absolutely no overlap. But the second piece does, and then I'll cleave it on the X part again, and then that part doesn't have anything to do with the overlap, so I'll put that in the basket. Now I still have this part. Now I have to go through the other axes on this part, this little sliver. I'll see where the overlaps are, and I'll cleave it where those are. So at most, I'll end up with 26 pieces.
If you chop twice on each axis, I guess.
Yeah, if I end something like that, because
Maybe.
it's 27 minus that one piece if that one piece was wholly encompassed in the other. So I was thinking, well, that's kind of dumb, because if it's wholly encompassed in the other, why even bother cleaving, right? Because it's an overlap, I might as well just ignore it. So I don't remember if I did or not, but I remember considering it and I was like, oh, is that too much mental math? Maybe, maybe not. I do remember that I think I ended up just deciding, you know what, let the computer handle it. It's a couple more cuts than it would be if it was just like a donut or, you know, on the side. But I did handle a case where if the first one was smaller than the second one, because there's nothing to cut on the second, the smaller one, right? Because it's wholly encompassed in the larger one. You can't cut the smaller one. You have to cut the larger one. But anyways, but that's my approach is I took one of these two cubes and I just started slicing away parts that didn't overlap.
Okay.
And then at the end of it, I'll end up with this giant list of cubes. And then I will get the volume of all of them. So let's get into the code. So the graveyard contains a whole bunch of code. But most notably, I had started by chopping up A's instead of B's, the first list instead of the second list. And okay, I realized that, oh, it's gonna really screw me over when I go to offs, because offs, I can't chop up offs. Offs are offs. I have to chop up the ons. So it's like, okay, I gotta do it the other way around. I have to chop up not the ones that I'm bringing out from the list, but the ones that are already in the basket are the ones that need to be chopped, because those are the ones that actually exist so far. And so I had to chop up the baskets. So I went back and chopped up the baskets. And so there was a bit of a shift in my things. But anyway, this first part, 76 to 92, is just me just getting the data prepped the way I wanted it to. Typically as, well, this one's a little bit different, but this is just a vector of numbers. And so kind of like yours, it's an array of numbers, right? Because it's got the X is the one part of the array, 2 elements. The Y is 2 numbers, and the Z is 2 numbers, and those are an array. But that's one array, so that's a vector of numbers. But then I also have that as a tuple that is the string in front, on or off, and that isn't a vector, which is the line. Every line has you know, a different thing. So this is the data structure that I was working with. So I have a vector, which is all the lines of the file. And every line is a tuple, where the first element of the tuple, or tuple, is the on or off, and then the second part is the vector of coordinates. So I have a function here called slice and dice.
What else would you name it? That's perfect.
Yeah, right. It's what it's essentially doing. Slicing and dicing. It does one at a time, and so you pass in where you want the thing to happen, or actually, I'm sorry, pass in where you want the thing to happen at an axis level. Is it the y-axis, the z-axis, x-axis, y-axis, z-axis? There's a number 0, 1, 2, or 3, 0, 1, or 2, and then the location in which you want the cut to happen, and then the cuboid that you want to cut, and then it just slices that one off and creates the 2 cuboids and passes the 2 cuboids over to you. So it's, you know, fairly simple. So most of the driving ends up in this for loop. And this for loop, essentially we get the list of all cuboids. And in my for loop, I take every line of the input and I start by, this is where it got kind of tedious for me in my control of lists. Because I have a list of the input. Then I have a list of the stuff in my basket, but then the stuff in my basket, as I pull it out and I chop it up, that ends up as a new list, right? Because I don't want to go back through my entire old list and chop up stuff that's like, or pass through possibly testing objects that have absolutely nothing to do with this current object I'm testing. I only want to test the object, the thing I'm chopping up. After I chop this thing up into, like, let's say 5 or 6 pieces, I don't want to put this into my list and then like go through the entire list again. It's really only these 6 pieces that are relevant to what I want, right? And even these 6 pieces, I get rid of the ones that have absolutely no possibility of overlap. Instead, I keep the ones that have overlapped, and then I see if that piece needs to be chopped up further or not. And so there's like lists of lists of lists. And so that was the kind of where I had to mentally take the time to figure out what pile am I going to put this stuff in. So I have this thing called the add cubes. That's one pile. I have this. I have a thing called new cubes, or I don't know. I guess I was able to get rid of new cubes. But then I have another one called temp cubes. But the add cubes is that temporary basket that I have. I think I have another list somewhere. I guess I don't. Wait a second. I don't think I have the most recent code because this one has no output. Give me 1 second. And I swear that there was another one called the new cubes because I had to keep track of only.
Well, I saw that new cubes commented out.
Yeah, and I tried to pull that out and it came back in because I wanted to reduce the number of lists because it was like just too many lists. I was like, oh, which list do I have to keep it in? When do I combine lists and stuff like that? But 1 second, let me pull again. Because this was actually the last one that I had done. Because I did thinking about it, I was like, oh, I don't want to think about it. The whole idea of chopping stuff up and like having stuff in a different place is just like, yeah. So yeah, so the code considerably grew.
Got a lot longer, yeah.
Okay, so, but the slice and dice got a little bit more complex. The slice and dice, I think, what was it? There was something that made this different because I remember I only had the one that you saw before, and then I had other cases in it. Exactly what it was that changed in the other cases. I don't know, maybe it'll come to me in another minute. I also had to sort my inputs. I realized that sometimes when I was slicing and dicing that the inputs or the numbers got reversed for some reason, which is odd. But anyways, the sorting was a simple fix for that one. I have another function called cuboid contains. This is again to try to see if I can avoid retesting if one is completely within the other. Because then I don't have to do so much testing on every axis. I just know that it's one is completely within the other, and I can either completely contain it, all right, it's there, or I can just, if it's an off, then I can just completely get rid of it from the original one. And then the axis contains is very specifically, does this one axis have anything that is wholly within the other one? And where does that fall in? I have an intersects function that checks to see where the intersections are in all three axes. And then, okay, so then here's my main function again, and the new cubes does come back in. And so I was like, Anyways, so I have the B cubes. Well, I changed the names because I started getting all these lists confused, but I have the B cubes and I have the all cube, or the all cuboid, which is the entire list to begin with. I have the B cubes, which are the B's, the ones after I've chopped them up, but this is the grand list after I've chopped them up. I have the new cubes, which is only the one after I chop one of the B's up into small pieces. And I have the temp cubes, and temp cubes is after I chop it up. I don't want to add it to my new cubes yet. This is just a function return, and the new cubes immediately end up in the new cubes. But the temp cubes immediately end up in the new cubes. Anyways, yeah, so I can chop them up more, right? But I don't want to chop up all of them. So sometimes I'll take some of them and I will just ignore it, but I'll only take the ones that got chopped up into smaller pieces, and I'll see, do I need to chop this up into smaller pieces or not? So yeah, so that's the kind of the idea with this one. So if I have intersections, then I'll chop them up. If I don't have intersections, I'll just add them right to the B cube list. So that in the future things, I can take this basket of B cubes and I can see what I need to chop them up based on the next one I pull off of the list. I have a couple of things that I test. One of them is if axis equals 4, which is kind of weird because there's not 4 axes, there's only 3 axes, but I reuse the number 4 to see whether or not it's wholly contained. Because if it's wholly contained, then I don't care, right? Unless it's off, right? But and then so that's the general idea of this entire for loop. I have baskets and I just pull one out of the list, see whether or not it's to be chopped up. Oh, I'm so sorry, that was the first one. Pull out of the list, pull one of the things out of the basket and compare it with this one, see if this new piece, this basket piece has an overlap with the new piece. And if it does, then I can chop this up. If not, put it back in the basket, take the next one, put it back in the basket until I find one that needs to be chopped up. And when I find one that needs to be chopped up, I take it, put that in a new basket, give it to the function, have it all chop it up, come back and look inside the basket, pull out all the ones that don't need to be chopped up any further because they have no more overlaps, take the one that's overlaps, put it in the function again, keep doing that until those get chopped up into smaller and smaller pieces, right? Eventually I'll have nothing that needs to be coming back, and that's when it's empty. And then I can say, oh, okay, so now these are the leftover pieces, and I take these leftover pieces and I dump them back into the overall list, and I get the next piece out of the list, out of the basket list, next piece out of the regular list, and I do that. Start doing that all over again.
I'm curious how many times your slice and dice function actually runs. If you could like put a counter in there to count how many times that function runs, it seems like it'd be a lot.
For the slice and dice?
Yeah,
Probably. All right, let's do that.
I'm just curious. Because every time you take a cuboid, you slice and dice it, then you take those little cuboids to see if they can be sliced and diced, right?
Right. It's the easiest way to do this.
I don't know how to do it in Rust.
And the problem is I can't do global functions or global variables. So I have to pass it in. And so
Oh,
you
that's
know
okay.
from
That's
where I
okay.
have to pass it in.
If it's not that easy, then.
So I have to pass it in from here and then from here, but this is the driver, I think. Right, there's no encompassing function for this one. Yeah, so this is the driver, so I can put it in here. So let's do it. So let num slices equal 0. Oh, that is not the right key.
Jump somewhere random in the code.
Yeah, because I hit
It's a
N for a
teleport.
match and it matched the next thing it found, which I get apparently is a 1. So I'll find we'll use that again. I don't know if we got num slices, but that's a mutable from variable because it's going to change over time. Slice and dice only should exist here, and I'll pass that on as a variable. But slice and dice already return something, so I'm going to have to add it as a reference variable so that it can change it and bring it back and after it's changed it. Then num slices, oh, but that is probably a large number, but why not just make a 64-bit so I don't have to worry about it. And I'm sure I can tune that down if I wanted to.
Probably won't be that big.
And then up here, we're going to accept a variable name. I'm just going to use the same one, which I almost invariably do, which is going to be a reference to a number, a 64-bit number. And then here I can finally, at some point, anywhere in here.
And print it somewhere.
Yeah, I don't think I ever do a short circuit return, so just before the return, I'll increment it. Num slices plus equals 1. I may have to own it so I can actually change the original version. So I have the star. We'll save that.
You've gotten pretty confident with Rust.
Man, it's
It's
a
fun
long
seeing
journey.
you actually write it.
Yeah, there's a lot to think
And
about.
hear you talk about how you're thinking about it too.
I will share my window.
Were you printing it anywhere yet?
I haven't run it yet. I'm gonna share my screen so you guys can actually see me do it. Can you see my entire screen now?
Mm-hmm.
Okay, so I'm running 22B. What is that? No default tool chain set. They have Rust installed on here, right? No override, no default. What's that even mean? I don't know what that means. I've never seen that before. No override and no default tool change that. Let's get back to this one.
Okay.
What can I? This is the first time I've ever seen this because most of the time. Tool chain, set default tool chain. Most of the time I just run this with Rust C. For some reason it doesn't want to run. Rust C is obviously installed because it's not like, I don't know what Rust C is, but okay, I'll have to see on this one. Sorry, I'll get back to you on that one. But anyway, so that's the idea with the mine.
Okay.
The approach that I have with mine. So a lot of chopping up, some testing that I pushed out to other functions. Otherwise, my loop would start getting like really ugly. Yeah. So there was a lot of things with the intersects, for example, to test whether or not from one was within the range of the other. So see whether or not the axis overlapped or not.
Yeah. I think with your approach, you had to care a lot more about ons and offs. The instructions matter a little bit more.
Yeah, the instructions mattered more, but for the only part where I really check to see whether or not it's on and off is down here, and that determines whether or not, because I've done all the chopping up.
Whether you add those
to your
basket or not.
So yeah, exactly. So do I add them or not? And if it's on, then I'll add them. If it's off, then no, I don't need to add them. They just get cut out of the older one. And then at the end of it, I calculate the volumes using, pretty much the same, right? X1 minus X2 plus 1, and then you multiply that by Y, same thing, Z, same thing. So that was it.
Oh, that was your last one of the year, right?
Yeah, that was the last one. I knew that it was going to be a lot of just like thinking and like doing a lot of things on each one of these, and so I didn't want to do it. So I saved this one for last.
I feel like this and 19 were the only ones that I felt the same way, where I didn't want to do them.
Yeah.
Every other question this year I had a great time with. I loved it. Well, we spent enough time on this. Should we go on to 23?
Let's go next one. Let's stop this and do you guys have any other questions on 22 before I move on? No? Okay.
Amphipods.
So this is one where they have a puzzle. Apparently they all like live like in caves or something like that. But there are a couple rules to the game of trying to move them all within a room of their own. So all the A's and B's and C's each have their own room that only they are supposed to be in at the end, right? They want to reassemble them. So you might start off with something like this, but you want to end up with something clean like that. And then the rules are, as you can see here, you can never stop in the space immediately outside of any room unless you're going to go into it.
But you can't stop there.
Right, you can't
you
stop
can go
there.
through that, but
Yeah.
you can't just hang out there while the guys move.
So you can't, a arthropod of a particular room, like say arthropod of a particular room, can't move into it until the room is filled with only of their kind.
Yeah.
And then
You can't go into another person's room.
And you can't go into another person's room.
You can start in another person's room, but you can't go into it.
Right. And then the third one is that it will stay in the spot until it can move into a room.
Yeah.
So once you put an
Amphipod.
amphipod out in the hallway or anywhere,
He can't move again.
They can't move again until they only got you got two moves.
Yeah.
You got one move to move somewhere, probably out into the hall, because you can't move into another room well, you actually no, I take that back. Maximum 2 moves.
Yeah.
One is either you can move up in the hall, or 2, you can move into your own room. But you can't move into your own room until that room is filled with only your kind. And so chances are you're gonna move into the hallway. Sometimes you might move into your own room. And then so yeah, I mean that pretty much sums up the
you have 2 moves,
the 2
maximum.
right?
And also each amphipod has its own energy level usage.
Right.
So A's are apparently the really young toddlers. They have tons of energy. So every time they move 1 space, it only costs them 1 energy. B's cost 10 energy to move 1 space, C's 100, and D's are the old grandpas that takes them 1,000 energy to move 1 space.
Yeah.
And you want to find the way. So how can you reorganize these guys using the least amount of energy?
Yeah. So you're kind of like pushed towards being very conservative with the moves on D.
Yeah.
Right. You really want to get the D's in their spots.
Yeah.
And then
It's less
worry about the other, shuffling the others. You don't really want to shuffle D's around if you can avoid it.
Yeah, these shouldn't just be sitting in the hallway.
So
that's that.
Yeah.
So did anybody write code?
I did not write code. I thought about writing code, but then I was like, it's faster if I just probably did this on paper, so I just did it on paper.
I tried to write code. I actually have like 200 lines of code that I've written that is not quite complete, but I feel like I'm on the right track. If I spend some more time on it, like maybe another evening or 2, I feel like I can get it, at least for part 1.
I think
Part 2, then I will have to modify my code and add a lot. And I feel like I'm on the right track, at least. If I can do part 1, then I'm confident that I could also do part 2 with just some additions to my code.
I think this is you could probably use Dijkstra for this one as well. There's a path, there's a limited number of choices, and there's an end that you want, and it's just a way of calculating how to get to that end that you want. And the cost is basically you want to minimize cost, so you want a priority queue prioritized to the least amount of energy. So I think it could probably be Dijkstra out.
Maybe.
Or something.
On the track.
Yeah, something along those lines. Anyways, you want to share what you had done? Do you have anything to show?
I have a
I didn't write code.
All right, let's see the GIFs.
Sorry, I'll go first. I'll share my GIFs and then.
I don't have anything actually to show. I didn't write code too.
Okay.
Okay, that's what I thought. I thought most of us probably didn't have code for this. So, but I made GIFs of what I actually did do. Actually, no, I do have something. Let me see. You guys can see my whole screen, right?
Yeah.
So let me go to day 22. Day 23, I did, I think, keep my file. Maybe, oh no. Oh yeah, okay. So I did part 1 in VS Code with just a text file, where actually I figured out the solution in advance, just on paper pretty much. And then I typed it out here just so I could screenshot everything and make a GIF. So I just copied and pasted and moved 1 element at a time. This is messy. This is a lot of
Is
copying.
that part 1?
Yeah, because part 1, I did only 1 move at a time. So for example, this A guy moved out into the hallway. And that's not even his final destination for this move. So I just wanted to show everything so that I could create this beautiful thing for you guys. Actually, I gotta open it up. The space bar here. Here we go. Can you see it? It's beautiful, isn't it? This is what I made. This is, yeah. Luckily, I think for part 1, I guessed the correct path my very first time. Based on all the constraints, where obviously you want to move D's as little as possible. C's probably be conservative also, and A's can pretty much go anywhere as long as they're out of the way. I was able to nail this one the first time. It didn't take too long. The rules were really restrictive.
Yeah.
So you didn't have too many options.
I think it took me 3 guesses to get mine. Because I did 1 and I was like, let's see, is it the one? And then I was like, oh, it's not the one. So I went back and looked for another path. I said, oh, okay, here's another path. There can't be another. Of course, again, it was too high. And I was like, what the heck? So I went back and poured over it again. And then, 5 minutes later, of course, I found even shorter one. At that point, I was like, huh, is this gonna be another one where I submit, it's gonna be telling me that the one? So then I spent like another 5-10 minutes just like, where are the other combinations? And then I said, all right, this is enough time. Yeah, I spent enough time and I pasted it in and I was like, oh, okay, this is the right answer. So, do we want? So I'll share.
I got it wrong.
Mine's. What's that?
Mine too.
Oh, yeah?
I got mine wrong too for quite a number of times, but at the end I figured it was off by 1.
Nah.
So
So
that
did
was
you
not
just-
easy to find.
Just change what you inputted?
At the end, yeah, but I tried, I think I got the wrong one, but it was weird because it was off by 1, like it was a toddler, you know, which was moving
it's an
1
egg.
extra.
Yeah.
Yeah.
The counting error, maybe?
So
Okay.
it's the same. I mapped mine as well.
You just
And then-
did each full move.
Yeah,
Okay.
I did a full
Yeah,
move.
that looks good.
So only 83 lines for mine, but
Cool. I like that we both chose the text files for it, essentially.
well, I figured you guys wanted to see something except like other than taking a picture of my napkin.
Yeah. Cool.
Yeah.
So, Farouk, you didn't have anything to show for part 1?
I think I have some writings, but
Yeah. And then part B for me, it's the same thing. Except
Well, we didn't talk about what is part 1.
oh,
Oh, okay. No, let's Farouk wants to show
this
it.
is,
Oh.
yeah, this is part 1. I think I erased mine as I go and I didn't keep track. So I
Okay.
just, I have some writings left, but not the entire map.
Yeah.
Cool.
Let's see the question then.
Right. Question for part B is just that they extends the depth of the pit, and so it adds a little bit more.
Yeah, so in this one, you unfold the paper, you find out that the paper that the Amphipods handed you was actually folded, and there's 2 rows in the middle that you did not have before.
Yeah.
So now, now instead of having 2 of each element, 2 A's, 2 B's, 2 C's, 2 D's, you have 4 of each one.
Yeah. So a lot more
And the
than-
same thing. You still got to find the most efficient path. But it's a little more complicated now because there's more options and more things going on.
You didn't check online, like how the other people have done it? You didn't try to
I
look
didn't
at
know,
it?
I didn't look about this one yet at all.
No, not yet.
Because I wanted to try to solve it first, because I'm trying to write the code right now. I can show you that after we show answers for part 2. So for part 2, I knew that doing it on paper or in a text file was going to be a little bit messy. So for this one, I did it in PowerPoint. I created, a PowerPoint screen where I created all the little blocks. That way I could easily just click it and drag it and move them around on there. And so just like before, I made a GIF for you guys. I thought you'd want to see it. So this one, I did not do every single move. I just did the final moves.
Mhm.
But you can see things going. Let me make it a little bigger. Yeah, you can see things going and my count going up. It was easy to drag and move things in PowerPoint to check all the different possibilities. This one took me a while. I think I had to try like 5 or 6 different times before I got the right one. And stupid me, of course, I tried the same thing like 3 times. I'm like, this one looks efficient. Oh, I already did that. So that was it.
Cool.
PowerPoint.
All right.
Yeah. Anybody else do something for this?
Nope. Mine was just another file, like I showed before. So
All
I
right.
don't know how interesting that is.
Do you want to see the code that I tried to write for this one?
Sure.
That isn't final, but you can look at it and tell me if I'm on a stupid path or anything. So I have a lot of code. It's pretty much just a ton of conditions, and I'm pretty much trying to write all the rules. So I'm adding conditions for all the different rule sets to stop if I, for example, go over too many moves or if I go into the wrong room. And then my plan is to just pretty much test all of the possibilities. So for a given amphipod, I'm going to choose him and I'm going to try moving him to everywhere that he can go. And then I'm going to choose all the other amphipods and just use recursion to grow all of these different branches, essentially, to see where they can go. So I created an input array like this. So I ignored the borders, like the top row and the bottom row, because no amphipods can go into there. They're just the walls. So I ignored the walls. And so this is my hallway. And then the room here. So that's the first layer of the room and the second layer. So in here I have my amphipods. I have B0 and B1, A0, A1. I wanted to keep them as individuals so that I could track each individual one and not get confused. So I gave them zeros and ones. I got a little bit messy. Next, I created an object to track the targets. So I want to know where does each amphipod have to be in the end. And each one can be, well, for the A element guys, they can be in these rooms. This is the I value, so the row, and the second value is the column. So A, for example, can be in row 1, column 2. So row 1, column 0, 1, 2. A can be in here. That's his final destination. Or he can be in 2, 2. He can go here. So pretty much A's, B's, C's, D's. Next, I added my multipliers for all of my different amphipods because, yeah, A's 1, 10, 100,000. And next, I created an array for my different amphipods because I want to get their index to use later for the different guys. And next, I like my 999s. So I'm going to try to get my total energy used. I'm just going to set it initially to an arbitrarily high number. And next, I created a few different functions. So my first function that I have here is my check finished function. So I'm just checking, are all of the amphipods that are in these locations, are they in their target locations? So I didn't use my target array for this one. I just checked individually. Is the guy in this array element an A? Is he an A? If anybody is not in their right spot, then I'm going to return false because I'm not finished. But if I am finished, then I'm going to get my total energy used. I'm going to see, is my new final energy lower than my total energy? If so, then I'm going to overwrite it. And I'm going to return true so that I can break out of my other function also. Next, I have a function just to calculate the energy it takes for each move. Because I'm pretty much going to jump, like I'm not moving 1, 1, 1, 1, 1. I'm going to jump like from this value to over here. So I have to calculate based on the original
points
composition, how much energy they had to use. And so, for example, it's a little bit complicated because my row, for example, they might start in the same row in a room and end up in a different row, or sorry, in the same row, but in a different room. So in that case, I'd have to count the horizontal path that they go, and the vertical would also be 1 up and 1 down to get there. Or maybe they start in this row and they end up a row down. So they got to go up 1 and down 2. So I have to keep track of that. It was a little difficult. I think it works okay. And then here's my main thing is my move amphipod function. Oh man, it's messy. So in here, I'm going to pass in my current amphipod. So that's going to be like A0 or A1 or B0. I'm going to pass in his index, his row, and his column. So amph I and amph J. Those are his row, that current amphipod's row and column. Next, I'm going to pass in the array. So I'm going to change the array for every time I call this function. I'm going to modify an array. And that's going to be this one, the array that shows where everybody actually is. I'm also going to pass in my moves. So I'm going to keep track of how many times each amphipod has moved individually, because they can't move more than twice. And I'm going to keep track of the energy that's used. And now this was just for printing to see where things are. That too. So next I'm going to get my amphipod type. So this is just going to be the first element of my amphipod. Is it an A, B, C, or D? I'm going to use that a lot later. And I'm going to get how many times has he moved? Has this amphipod moved 0 times, 1 time, or 2 times? And so I have a lot of conditions here that I can return on. So if this condition is met, then this branch is getting cut off because it's not possible. So if he's moved more than once already, that means he's already moved twice, then he can't move again. So I'm going to return. If he's already in his target location, then he doesn't need to move. If both of the amphipods are already in the correct room. So this one I'm checking if he's in the bottom room in his row, I think. No, what am I doing? Yeah. So I'm checking if he's in the bottom room, then he's already in the correct room. He doesn't need to move. If both of them are in the correct room, so that means the one in the bottom room is the correct type, and this current amphipod is in the room right above him, he's in the correct type. So then we can return also. If he's blocked in and can't move, so if he's at the bottom and there's an amphipod of a different type on top of him, he can't get out. Next, I'm going to check left and right from his room to see if any amphipods are blocking the hallway. So I want to see how far left can he go and how far right can he go. So I created an array for a range. This range is going to have all of the possible range, like areas that he can go to. But I think I messed up in here because actually these ones are okay. So I'm looping to the left, starting from my current amphipod's column value to see if he can go there. That's why I'm breaking if my element in that location is not a dot. And so I'm just going through the hallway to the left. And if he can go that way, I'm going to push that into my range, that value. And I'm doing the same thing looking right to see where can he go. But I think I messed up in here. I have an issue because I'm not passing in the values that are directly in front of a room because they can't stop directly in front of a room. So I'm ignoring 2, 4, 6, and 8, which I think is why I just realized this is why I'm having trouble for my next part, where I'm checking if they can go into their own room. So I'll get to that. The next thing, I have another check where if there is no range, that means there's probably an amphipod blocking them on the right and on the left. So he can't get out of his room, he can't move. So we can return. Next, I'm going to sort my range just to make sure I'm going in order. And yeah. So now I'm going to check pretty much, can he go into his room? If he can go into his room, I'm going to see which area in his room can he go? Can he go all the way to the bottom of his room, or can he only go to the top of his room? And then if he does that, I'm going to calculate how much energy was used in order to get there. And I'm going to see, is this round finished? Is he the last guy to get into his room? But I think this whole thing is not working because I'm checking if my range includes my target column, but it will never include my target column because I can't have that target column in my range. So I need to rethink this one a little bit. Maybe I need a separate array or just have a separate where I can add these columns into my range and just handle later where they can't stop there. I think I need to do that. I think that's where my bug is right now. So now I have a variable for went into room. So I'm tracking, did he go into his room? I'm gonna start it as false, but if he goes into his room, I'm gonna set it to true. And then for my next part, I'm gonna check. If he didn't go into his room, then I'm gonna try to move him into a hallway. Because by now, when I get to this point, I know that he can move. So if he can't move into his room, then he should be able to move into the hallway somewhere. So now I'm gonna loop through all of the different areas in my range, and I'm gonna check. I'm gonna pretty much move him into that area, and then call my recursive function for all of my other amphipods. Now this guy's moved. I'm gonna change his location in my array, and I'm gonna call my move amphipod function with all of my other amphipods with passing in my new array and my new energy used. And I have an else also, because this is if he didn't go into his room, I'm gonna move him into a room and then do something else. If he did go into his room, then I'm just gonna still call my recursive functions for all the other amphipods, but I don't have to move this current amphipod again, because he's not gonna move twice if he can already go into his room. So I think that this is gonna work eventually. I'm gonna tweak it a little bit more. I realized that one major bug where my range doesn't allow him to go into his room. And then I need to update this one later too, because right now I'm only calling my initial function with my A0 amphipod. I need to update this later to call my initial function with all of the possible amphipods, the guys who are at the tops of their rooms. So I'll just have to loop through that row, and if it's an amphipod, I'll call this function with him. What do you guys think? Does it have potential to work? Or too sleepy to care? I don't know. I wanted to work on it. See if I
Nice
could
try,
do it.
so
Yeah.
nice you tried
Yeah.
actually coding it.
I think that it will work if I just fix a couple bugs, because I think I have all of the conditions to like cut off a branch. So I think it'll kind of keep it pretty contained, where there's not going to be that many possibilities. They only have a few different places that they can move, and it's easy for a branch to get cut off. There's a lot of different conditional checks I have.
Yeah. I mean, the way I thought of it was each room is its own cube. And then the hallway is its own interesting data structure where only things can exist at certain spots. And other than that, I was going to just write a recursive function. And the only key to this recursive function was to try to eliminate stupid moves so that it doesn't run every single possibility, but eliminates the obviously wrong possibilities. That was about it. I was going to run it and see what happens.
If you end up actually coding it, I'm curious to see it.
Okay.
I couldn't completely understand if you don't want to though, because you've already finished.
No. Yeah, I'm also trying to finish 2015 at this point. I think I only have one left to 2015 now.
Oh, wow.
Yep, cool.
Nice.
All right.
I think other than that, now we only have one day left. We got Friday left for 24 and 25s. So it's, I guess, kind of interesting to see that we have a puzzle here that none of us wanted to, well, other than Scott wanted to program. Because somehow
it was easy enough by hand. Like,
yeah,
I
easier to
did
do by
by
hand. So I was like, oh, after especially the last couple
Yeah.
of days of like these long ones, 22 was just like after 22 or the first part of 22 and the second part, just reading the second part of 22, I was like, all right, I'm not gonna do this one.
This is the last one that I've even tried. I didn't even start this until a couple nights ago.
Oh, programming it.
Yeah, because I got the answer on paper way before. So I went on to the ones that I didn't finish yet first.
And it was one of those things where, because a lot of these I'll start on paper. A lot of these I'll start, just jotting down ideas and approaches. And then, but this one, like I jotted down and I was like,
You can do the whole thing.
like I'm
on
halfway
paper.
there. So just finish it. Of course, I got a couple of wrong answers out of it, but I mean, I figured like, oh, there can't be that many possibilities, especially with, like you said, with the restrictions on it. So I was like, yeah, I'll just.
You had mentioned before that you got the complete answer for one of the days on a calculator. Basically, that had to be the projectile one, right?
It was a projectile. The first day of the projectile one, I just got on a piece of paper and I was like, okay, now how do I code this? And I knew I wanted to use Gaussian sums because that's basically what easiest way to get projection as it slowly grew over time. But yeah, I just kind of thought about it and I was like, oh, can this be really a day? What was that? 16, 18, something like that?
Yeah, 17 or 18.
Yeah. So I was just sitting there fiddling around with a REPL. I think I was just using like a PHP REPL to do the math. And I was like, oh, is that the answer? Like, it can't be the answer. I pasted it in. I was like, oh my God, that was the answer.
Wasn't hard. That was just for part one though, right?
Yeah.
Part two, you had to code a little.
Part two had to code.
All right.
But a lot of the stuff still transferred over. So yeah, it was one of those weird days where I was like, oh, is this really it? But yeah, and then this day too, it was just kind of like, oh, I did this on paper. That's weird. But now that you're approaching it with programming, I can see why, if we try to do it programmatically, it could be a little more complicated.
I think it's the way I'm going about it, it doesn't seem that hard. It's just very procedural. Like
Yeah.
I'm checking this and then checking this and this.
Right.
Like I'm just doing it like step by step. I think I'm on the right track.
Yeah, I mean, I was gonna do a similar thing, right? Recursion with cutting off, the key thing is trying to cut off branches, because the problem with recursion, especially with games, is just usually is the sheer number of possibilities.
Yeah.
It's hard to calculate, and so
Narrow it down.
yeah, find ways to optimize the recursion, and whether it's either frequency counting using state, or just finding and being really aggressive about cutting off dead ends. Is one of those three I find is a way to solve those with recursion.
All right. Only 2 days left.
Cool. So we'll see you guys then on Friday.